This is a GCSE chemistry tutorial looking at the reactivity series, displacement reactions and redox. It fits into chemistry topic 4. In this tutorial we will look over the reactivity series, we will look at displacement reactions including the reactions of metals with acids and water, we will look at redox, we will look at the extraction of metals, the future of copper and alternative ways to extract it, as well as looking over half equations. In this tutorial video we will look at the fact that some metals are more reactive than others. We will look at why potassium can displace iron but copper can't, and we'll have a look at different ways to extract metals. Our big question for this part of the tutorial looks at why wedding rings are made of gold and not of potassium. So what is the reactivity series? Well, the reactivity series is a list of how reactive different metals are. The most reactive metal on our reactivity series is potassium. Other very reactive metals are things like sodium, calcium, magnesium, the group 1 and then the group 2 metals. We pop carbon in as well, even though it is a non-metal. This is to do with how we can extract different metals, which we will look at in a few minutes. Below carbon we have things like zinc, iron and lead, and then finally down to the very unreactive metals, copper, silver and gold. Most metals aren't found as pure metals in the Earth's crust. Most are found as ores. An ore is a rock containing a metal compound, often known as a mineral. Most metals are quite reactive. Therefore, they will react with oxygen to form oxides. For example, iron ore, which contains iron oxide. This needs to be concentrated down from the ore to its metal compound, and then finally can be reduced in order to form iron. In order to extract metals, we need to first concentrate them to remove everything but the metal compound, and then we need to reduce them or put them through reduction in order to remove the metal from its compound. You do not need to learn the names of any ores, however, some common ores are listed here for your notes. How we extract a metal depends on its position on the reactivity series. Silver and gold at the bottom, the least reactive metals, are often found natively, as in they are found as a pure metal and do not need to be extracted. All of the metals below carbon can be extracted using reduction, which this tutorial video will focus on. These include copper and iron. Any metal above carbon has to be extracted using electrolysis. We will look at electrolysis further in an additional tutorial video. This means that the two main extraction methods are reduction and electrolysis. Reduction we will look at in this tutorial video, electrolysis we will look at in another tutorial video. So what is reduction? Before we can look at reduction, we first need to look at redox. When compounds lose or gain oxygen, they go through a redox reaction. This means that either they have been reduced or oxidized during the reaction. If we have a compound being reduced, then another compound must be oxidized in the same reaction. Oxidation is the addition of oxygen to a substance, whereas reduction is the removal of oxygen from a substance. In the reaction here, where we have lead oxide and carbon, forming lead and carbon monoxide, the lead oxide has been reduced, it has had oxygen removed, whereas the carbon has gained oxygen, therefore it must have been oxidized. Looking at the three reactions below, I want you to pause the video and decide whether these are examples of reduction or oxidation. For our first reaction, we have carbon reacting with oxygen to form carbon dioxide. Oxygen has been added to the carbon, therefore this is an oxidation. In the second reaction, carbon dioxide has broken down into carbon monoxide and oxygen, carbon dioxide, 2 oxygens, monoxide, 1 oxygen. We've got a loss of oxygen, therefore a reduction. And finally, we have hydrogen peroxide, which is H2O2, forming water and oxygen, water, H2O. In going from H2O2 to just H2O, we have lost oxygen, therefore this is also a reduction. Reduction can therefore be used to extract metals. Any metal below carbon can be reduced from their ores by using carbon. This is better than electrolysis for these metals because it is much cheaper than electrolysis. This happens as the carbon is more reactive and therefore can displace the metal. Which leads us on to the question, what is a displacement reaction? A displacement reaction is where a more reactive element takes the place of a less reactive element. You may remember displacement reactions from when we looked at the group 7 halogens. For example, here we have a single displacement, where we have A reacting with the compound BC. A is more reactive, it can displace B, forming the new compound AC and leaving B by itself. In the case of extracting metals, if A was carbon and BC was iron oxide, then we can use the carbon to produce carbon dioxide, leaving the metal by itself. Here are 2 examples. So potassium plus zinc chloride makes potassium chloride and zinc, whereas sodium plus potassium sulfate we get no reaction. Why? Well, simply, in the first case, potassium is more reactive than zinc, therefore it is able to steal the partner and form potassium chloride, leaving zinc by itself. In our second reaction, sodium is not powerful enough to displace potassium, therefore no reaction occurs. We can also include hydrogen into the reactivity series. Hydrogen fits above iron, but below zinc. It is less reactive than carbon. This allows us to work out if a metal will react with an acid. If the metal is more reactive than hydrogen, then a displacement reaction will take place and the metal will react with the acid. Some metals are able to react with acid in order to produce a salt and hydrogen gas. The speed that this reaction occurs at is determined by the reactivity such as the metal. Therefore, very reactive metals such as potassium, sodium and lithium will react explosively, whereas less reactive metals such as magnesium would react steadily but not explosively. Moving further down, zinc and iron will react far less violently, whereas copper won't react with cold dilute acids. This shows us a decreasing level of reactivity of the metals. At the top of the reactivity series, we had our explosive reactions. Moving further down, the reactions are vigorous but much less reactive. Moving on to zinc, it's a very slow reaction, and then finally copper shows no reaction at all with cold dilute acid. Some metals can also react with water to form metal hydroxides and hydrogen, as we looked at when we looked at the group 1 metals in the groups of the periodic table. The metals that can react with cold water are all found at the top of the reactivity series. These are the group 1 metals and calcium. Magnesium can, however, react with steam. Less reactive metals, for example zinc, iron and copper, aren't able to react with water to produce hydroxides. When we're talking about the extraction of metals, we can link this to the Earth's resources topic. In the Earth's resources topic, we talk about the future of copper. This here is a useful graph showing us how much potential copper is left. Copper is here, with copper mines set to run out by about 2050. This means that reducing copper ore to form copper is not going to be viable in the future. One potential method would be to use electrolysis. Electrolysis, however, is very expensive. We will look at electrolysis in another tutorial video. So what are alternative ways of getting copper? The first method we can use is known as phytomining. In this technique, we can use plants because plants absorb copper compounds into their roots from the soil. These compounds then get concentrated in the roots so that we can collect them. To collect them, we must burn the plants in order to turn the roots into an ash. This ash then contains the copper compounds. This ash can then be reduced to remove the oxygen, forming our pure copper. This method obviously has downfalls as we are burning plants and therefore releasing CO2 into the atmosphere. A second potential method is known as bioleaching. Bioleaching uses bacteria rather than plants. In this, we use bacteria that can absorb copper compounds. These bacteria produce solutions called leachates, which contain these copper compounds. We can then purify this leachate in order to get the copper, extracting it further through electrolysis. We can also use scrap metal refining. In this, copper can be extracted from copper salt solutions using scrap iron. Why? Well, simply because iron is more reactive than copper, so it can displace it. For example, copper sulfate plus iron will form iron sulfate and leave us with our pure copper. We can therefore combine these methods in order to avoid having to extract more copper ore. So we grow plants in soils containing copper compounds, burn the plants, producing an ash. We can then leach or bioleach this into a solution containing copper compounds. We could also reduce this ash to get the copper. We can also take low-grade ores, again leaching or bioleaching them, in order to create this leachate. That leachate can either be displaced using scrap iron, or we can carry out electrolysis in order to form our copper metal. Using what we have looked at both in this tutorial as well as in previous tutorials, I want you to finish the word equations and write symbol equations for the following. For our first one, we have magnesium and sulfuric acid making magnesium sulfate and hydrogen, with the balanced symbol equation being Mg plus H2SO4 goes to MgSO4 plus H2. Our second equation, zinc oxide plus hydrochloric acid, would make zinc chloride and water, as this is a neutralization reaction. The balanced equation being ZnO plus 2HCl goes to ZnCl2 plus H2O. And then finally we have potassium plus water, making potassium hydroxide and hydrogen. The balanced equation being 2K plus 2H2O goes to 2KOH plus H2. So far, we have looked at both word and chemical or balanced equations. The word equation being, for example, aluminium plus iron 3 oxide goes to aluminium oxide and iron. The chemical or balanced equation, 2Al plus Fe2O3, goes to Al2O3 plus 2Fe. In this last bit of the tutorial, we're going to look at two more ways of writing equations. One will be ionic equations and the other will look at half equations. Half equations will be looked at again in the electrolysis tutorial. So what do we mean by an ionic equation? Well, ionic equations only show us the ions that we're interested in. This means we can remove the other ions from the equation. The ions that we remove are known as spectator ions. Ions are always present when something is in the aqueous state. Ionic equations are particularly important when looking at displacement reactions. For example, we have magnesium and copper sulfate going to magnesium sulfate and copper, a nice simple displacement reaction between the magnesium and the copper. So what ions are present in this reaction? In this reaction, we have 3 ions present. We have our copper, our Cu2+, our sulfate, our SO42-, and our magnesium, our Mg2+. Our reaction looks as follows. Magnesium as a solid with no ions are present, plus copper, a 2+ ion, and we've got the sulfate ion present as well, magnesium plus copper sulfate. Goes to magnesium sulfate, we've now got magnesium 2+ and SO42-, and copper, which is no longer an ion as it is in the solid state. So which ion doesn't change at all? Well, this is our sulfate ion. This makes our sulfate ion into a spectator ion. This means it stayed exactly the same, so it hasn't taken part in the reaction. It swapped partners, but it hasn't changed in any way. This means that our finished ionic equation is Mg plus Cu2+ goes to Mg2+ plus copper. This shows a movement of electrons between the magnesium and the copper, with 2 electrons going from the magnesium to the copper, leaving us with magnesium 2+ and copper with a neutral charge. There are 2 further questions for you to have a go at here. We can also link redox to ionic equations. Previously, we looked at redox being a loss of oxygen for reduction and a gain of oxygen in oxidation. Whilst this is definitely true, we can also use reduction and oxidation to mean something slightly different. We can also talk about redox in terms of electrons. In this case, oxidation is a loss of electrons and reduction is a gain of electrons. This allows us to use OILRIG. Oxidation is loss, reduction is gain. So looking at our example once more, what has been reduced or oxidized in this example? So magnesium has been reduced as it has lost electrons. It has become a positive ion, therefore it has lost electrons. Copper, however, has been oxidized as it has gained electrons. It's gone from being a positive ion to being a neutral ion, therefore it must have gained a negative charge. That negative charge has come from the electrons. As before, have a look at your other 2 examples to work out what has been reduced and what has been oxidized. You should notice that the metal being reduced is the more reactive metal, the one that is higher up in the reactivity series. The metal being oxidized is the metal that is lower down in the reactivity series. We can also link ionic equations to half equations, which are the final type of equation you need to be able to write. In these, we're only interested in what the electrons are doing. Continuing with our example, we can look at the change between magnesium as a solid and magnesium 2+ ions in an aqueous solution. We've already looked at this being an example of reduction. It has been reduced as it has lost electrons. These are given off in the reaction and therefore are put on the product side. This means that the half equation for this reaction is Mg solid goes to magnesium 2+ as an aqueous solution plus our 2 electrons, our 2E-. This means that both sides of the equation are balanced as the overall charge on both sides is 0. We have an atom on this side with a charge of 0, an ion on this side with a charge of 2+, but we also have our 2 negative electrons. What about oxidation? I want you to pause the video now and have a go at writing the half equation for our copper. So what about our copper? Well, we already know that this is an oxidation reaction, as the copper is gaining electrons. As the copper has been oxidized, we know it's taking in electrons. This means that the electrons are put on the reactant side as they are being added to the copper 2+ ion. This means our half equation is Cu2+, our aqueous ion, plus our 2 electrons, forming our copper solid atom. As with the previous half equation for reduction, the charge on both sides is equal at 0. We have a 2+ ion gaining 2 electrons, making 0, and our atom which has a charge of 0. It is important to note that when writing half equations, both half equations must be balanced with each other. This means that if one of your half equations were to lose 1 electron, whereas the other gains 2 electrons, then you would need to balance them so that both of them are transferring a total of 2 electrons. We will look at half equations more in the next video on electrolysis.